Good day, everyone. I am April Joy Lope, and I am going to discuss the topic number 1, which is the main type of methodologies in the assessment to the desirability in economic and environmental or social aspect of constructing a highway proposal. I will be focusing on the economic appraisal of highway schemes. Economic appraisal of highway schemes. At various points in the development of a highway project, the developer will require economic assessments of the route option under consideration. In economic analysis, financial units like pounds, euros, dollars are used as the tangible basis of evaluation. Economic appraisal techniques can be used to justify a scheme in absolute terms in which cause the decision is made on the basis of whether the project is economically efficient or not. Cost-benefit analysis. This utilizes the net present value technique where the costs and benefits of the scheme are discounted over time so that they represent present-day values. Using this method, any proposal having a positive net present value is economically sustainable in absolute terms. Identifying the main project option. This is the fundamental step in the cost-benefit analysis process where the decision makers compile a list of all relevant feasible options that they wish to be assessed. Finding sound feasible option is an important component of the decision process. Identifying all relevant costs and benefits. Many of the benefits of improvement to transport project equates to decrease in cost. One of it is the reduction in vehicle operating costs. If there's a newly upgraded project, it will lead to lower level of congestion and higher speed than the already existing roadway. This usually results in lower fuel consumption and lower maintenance costs due to the reduced wear and tear of the vehicles. The second one is the savings in time. Of course, if there's a newly upgraded highway, it may less or reduce the travel time and as well as improve the different travel services. And the last one is the reduction in the frequency of accidents. The cost for the property damages and personal injuries and as well as fatal accident may be reduced since there's already a newly highway projects. Economic life, residual value, and the discount rate. A highway project is often complex and long-term. A certain project has a time slot wherein you must finish that project on that given time since there's already a cost and benefits estimated for that project. The project may well have to be assigned a substantial residual or salvage value reflecting the significant benefits is still to be accrued from the project, or conversely, cost is still liable to be incurred by it. The other one is the discount rate, which translates all costs and benefits to time equivalent values. It is a collective discount rate reflecting a project of benefits to a large number of people and spanning a time frame greater than one full generation. Use of economic indicators to assess basic economic viability. There are three different techniques used to assess the economic viability. The first one is the net present value, which estimates the economic growth of the project in terms of the present worth of the total net benefits. The second one is the internal rate of the return, which will give for each option under consideration the rate at which the net present value for it is equals to 0. And the third one is the benefit cost ratio, which ratio is based on the ratio of the present value of the benefits to the present value of the cost. Advantages and disadvantages of cost-benefit analysis. Cost-benefit analysis is most suitable for ranking or evaluating different highway options rather than for testing the absolute suitability of a project. The advantage of it is the use of common units of measurement, money, facilitates comparisons between alternative highway proposal and hence aid the decision-making process. The other one is it offers a broader perspective than a narrow financial or investment appraisal concentrating only on the effects of the project on the project developers. The disadvantage of this is that if the decision was based on economic factors only, an incorrect decision may result from the confusion of the original primary purpose of the proposed project. The second one is the method is more suitable for comparing highway proposal design to meet a given transport objective rather than evaluating the absolute desirability of one project in isolation. Payback analysis. Payback analysis is an extremely simple procedure that is particularly useful in evaluating proposals such as privately funded highway projects, where tools will be imposed on user of the facility in order to recover construction costs. It is more usefully applied to projects where the timescale for equalization is relatively short.
Good day, I'm Louel Pelaez, and this is the continuation of Topic 1, Environmental Appraisal of Highway Scheme. While the cost-benefit framework for a highway project addresses the twin objective of transport efficiency and safety, it makes no attempt to value its effects on the environment. Environmental evaluation therefore requires an alternative analytical structure. The structure developed within the last 30 years is termed Environmental Impact Assessment, EIA. So, dapat kapag magbibuild tayo ng highway or daan, dapat wala tayong masasagasaan na mga living things like trees, etc. Basta wala tayong madadamage anumang environment. The National Environmental Policy Act 1969, which requires the preparation of an Environmental Impact Statement, EIS, for any environmental significant project undertaken by the federal government. NEPA prescribes a format for the EIS requiring the developer assess the probable environmental impact of the proposal, any unavoidable environmental impacts, alternative option to the proposal, short-run and long-run effects of the proposal and any relationship between the two, any irreversible commitment of resources necessitated by the proposal. So, dito sa Philippines, ang nag-collab ay ang DNR at DPWH. Alam naman natin, ang DPWH, ay ang concern nito ay sa mag-build ng mga daan or mga highways. While ang DNR, required, ang gawain nila ay sila nagkabigay ng permit kung alin ang puputulin mga puno or gagalawin mga puno, etc. The directive also details the minimum information that must be contained within the EIS. This includes, number 1, a physical description of the project. Number 2, a description of measures envisaged to reduce remedy the significant adverse environmental effects of the project. Number 3, the data required to both identify and assess the main effects on the environment of the project in question. Within the UK, since 1993, the Design Manual for Roads and Bridges has provided the format within which the environmental assessment of highway scheme has taken place. It identified 12 environmental impacts to be assessed for any new improvement trunk road proposal. So, noong 1993, nag-propose ang UK ng bagong format or nag-identify sila ng 12 environmental impacts na kailangang isang alang-alang mo pag magagawa ka ng mga roads and bridges. So, these are the 12 environmental impacts na dapat isaalang-alang mo kapag mag-design ka ng roads and bridges within the environment. Number 1, air quality, cultural heritage, construction disturbance, ecology and nature conservation, landscape effects, land use, traffic noise and vibration, pedestrian, cyclist and community effects, vehicle travelers, water quality and drainage, geology and soil, policies and plans. So itong makikita natin ay Table 3.6, Appraisal Groupings. So ito ang appraisal groupings, local communities, travelers, cultural, national environment. Ito yung magiging impact sa kanila. Demolition properties, noise, visual impact, severance, etc. The new approach to appraisal, NATA. During the late 1990s, the UK government reviewed its road program in England and identified those strategic strategically important schemes of capable of being started within the short to medium term and listed them as a potential candidates for inclusion within a target program. This appraisal summary table, AST, is designed for presentation to those decision makers charged with determining whether approval for construction should be granted, and if so, what level of priority should be assigned to it. It thus constitutes a key input into the process of scheme approval and prioritization. The AST summarizes the assessment of the scheme in question against the following 5 objectives and their constituent impact, seen by the government as being central to transport policy: environmental impact, noise, air impacts, landscape, biodiversity, heritage, and water, safety, economy, journey times, cost, journey time, reliability, regeneration, accessibility, pedestrian, access to public transport, community surveillance, integration. So, topic 2, basic elements of highway traffic analysis. The functional effectiveness of a highway is measured in terms of its ability to assist and accommodate the flow of vehicles with both safety and efficiency. In order to measure its level of effectiveness, certain parameters associated with the highway must be measured and analyzed. These properties includes: number 1, the quality of traffic, the types of vehicles within the traffic stream, the distribution of flow over a period of time, usually 24 hours ito, the average speed of the traffic stream, the density of the traffic flow. Speed, flow, and density of a stream traffic. As we can see, equation 1 is equals to Q is equals to N over T, wherein Q is a measure of the volume of a traffic on a highway. In general terms, Q is expressed in vehicles per unit time. The number of vehicles on a given section of highway can also be computed in terms of the density or concentration of traffic as follows. K is equals to N over L, where the traffic density K is a measure of a number of vehicles, N occupying a length of roadway. For a given section of road containing K vehicles per unit length, the average speed of the K vehicles is termed the space mean speed U. Therefore, U is equals to 1 over N summation of Li, N, I is equals to 1 over T, where Li is the length of road used for the measuring the speed of any vehicle. It can be seen that if the expression for Q is divided by the expression for K, the expression for U is obtained. U divided by K, N over T divided by N over L is equals to N over T times L over N is equals to L over T is equals to U, which is equation number 4. Thus, the 3 parameters U, K, Q are directly related under stable traffic condition. U is equals to UK. This continuates the basic relationship between the traffic flow, space mean speed, and density. Speed-density relationship. In a situation where only one car is traveling along a stretch of highway, densities will by definition be near to zero. As we can see in figure 1, this shows the illustration of speed-density relationship. Along x-axis, we can see that density as vehicle over kilometer. We can see in y-axis, speed is equals to kilometer per hour. In mathematical terms, this linear equation gives rise to the following equation. U is equals to UF 1 minus K over Kj, wherein U is equals to space mean speed, UF is equals to free flow speed, K is equals to density, and Kj is equals to jump density. Flow density relationship. Combining equation 5 and 6, the following direct relationship between flow and density is derived. Q is equals to UK as UF 1 minus K over Kj times K. Therefore, Q is equals to UF K minus K squared minus Kj, which shows equation number 7. Figure 2 shows the illustration of flow density relationship. As we can see, we form a semicircle. In order to establish the density at which the maximum flow occurs, equation 7 is differentiated and set equal to 0 as follows. dq over dt is equals to uf 1 minus 2k over kj is equals to 0. Since uf is not equals to 0, the term within the bracket must equal 0. Therefore, 1 minus 2km over kj is equals to 0. Thus, km is equals to kg over 2, which shows equation number 8. Speed-flow relationship. In order to derive this relationship, equation 6 is rearranged as k is equals to kj 1 minus u over uf, which shows equation number 9. By combining this formula with equation 5, the following relationship is derived. Q is equals to UK, so Q is equals to KJ U minus U squared over UF, which shows equation number 10. This relationship is again parabolic in nature. As we can see, figure 3 is the illustration speed flow relationship. In order to find the speed at maximum flow, equation T is differentiated and put equal to 0. dq over dt is equals to kj, 1 minus 2u over uf is equals to 0. Since kj is not equal to 0, the term within the brackets must equal to 0. Therefore, 1 minus 2um over uf is equals to 0. Thus, um is equals to uf over 2, which shows equation 11. The speed at maximum flow, is thus equal to half the free flow speed. UF, its location is shown in figure 3. Q is equals to times Km is equals to UF over 2 times Kj over 2. Therefore, Qm is equals to UF Kj over 4, which shows equation 12.
Good morning everyone. My topic will start in the determination of the capacity of a highway. In determining the capacity of highway, we do have two different approaches. One is the level of service approach, and the second approach is mostly used in Britain, which puts forward practical capacities for roads of various sizes and width carrying different types of traffic. Unahin natin ang level of service approach. Ito yung approach kung saan tinitingnan yung viewpoint ng mga road user. So ito ay tinitingnan nila yung level ng congestion sa highway sa pamamagitan ng variables tulad ng travel time at traffic speed. Meron ako ditong tatlong definitions na gagamitin natin sa pagdetermine ng roads level of service. Ito ay ang hourly volume, denoted by V, peak hour factor, denoted by PHF, and service flow, SF. So meron din silang kani-kaniyang formula na pwedeng gamitin para makuha. Another topic that I am going to discuss is about the maximum service flow rates for multi-lane highways. So dito, nag-generate naman ang highway capacity manual ng maximum flow values. Ito namang mga values na kanilang ginawa ay para lamang sa ideal conditions. So meron tayo ditong formula na SF max is equal to CJ times V over C times N, kung saan yung CJ is the capacity of standard highway lane, then yung J is the design speed, then V is the hourly volume times N, which is the number of lanes. Let us have an example. So given doon sa example, yung value ng V at saka PHF. So kukunin natin yung service flow, then makakakuha tayo ng 2,312.5 vehicles per hour. Then mula doon, kukunin natin yung maximum service flow by inputting this in the formula. Then makukuha na natin yung level of service na provide ng highway. Sa non-ideal conditions naman, nagkakaroon tayo ng mga adjustment factors such as F of W, FH of B, F of P, and F of E. Ito yung kapag hindi na, kumbagay, lumampas na rin sa given na conditions. Halimbawa, nag-set tayo ng 3.65 meters as standard. Then, yung lane widths ay naging narrower or mas greater dun sa 3.65. So, nagkakaroon na tayo ng adjustment factor. So, makikita sa table yung mga correction factors para sa non-ideal lane widths and clearances para sa obstruction. So, isa pang nakaka-apekto sa passenger car equivalent ay yung mga 3 different class ng terrain, kung saan yun yung level, rolling, at mountainous terrain. So, meron din ako ditong table na meron ang correction factor na equivalent ng passenger car para sa different classes of heavy vehicles. So, kapag na-obtain na natin yung necessary PC evaluation, nagkakaroon na tayo ng overall correction factor. So, magkakaroon tayo ng formula na FHB is equal to 1 over 1 plus PT multiplied by ET minus 1 plus PB multiplied by EB minus 1 plus PR minus ER minus 1. Dalawa ding table na ito, nagpapakita naman ito ng correction factors para sa driver population types at para sa highway environment. So, ito yung ginagamit kapag nagdedetermine na tayo sa problem. Sa an example problem. So, given yung PT, PB, at PR, i-input natin sa formula ng service flow. Then, ililipat natin doon sa kaninang nag-arrive tayong formula. Then, makukuha na natin yung level ng service na in-offer nung section ng highway na yon. Another topic is the maximum service flow rates for 2-lane highways. So, meron tayo ditong formula na SF divided by 2A times V all over C. Meron din tayong mga ideal conditions na sinusunod. Meron tayong 7 conditions. Then, let us proceed with an example. So, from the problem, given yung PT, PB at PR, then yun daw terrain is rolling. So by substituting the value in the formula na kanina, yung FHB, value ng FHB, makukuha natin 0.657. Then ilalagay natin siya doon sa formula ng may adjustment factor para sa non-ideal conditions. Then mag-a-arrive tayo sa answer na 1145 V all over H. Our topic is about sizing a road using the highway capacity manual approach. So dito nagkakaroon tayo ng formula na DHB is equal to KI times AADT. So where KI corresponds to its highest annual hourly volume. So since yung DHB is a two-directional flow, so yung directional design or volume which is the DHB ay may estimate natin or ma-obtain by multiplying it to the directional factor D and also to the value of K. As we will have the formula DDHB is equal to K times D times AA dt. Another example. So para sa solution nito, gagamitin natin yung formula nung DDHB is equal to K times D times AA dt. So since given naman yung mga value nun, i-input lang natin. Then makukuha na natin yung value which is 2880 V all over H. So yung V ayun yung hourly volume. I-input naman natin para makuha natin service flow given the PHP or the peak hour factor. Then i-input natin doon sa non-ideal condition kanina na merong mga adjustment factor. Then makukuha na natin yung tinatanong which is the required physical extent of the highway. The last topic would be about the estimation of AADT for a rural road in its year of opening. So, sa pag-select ng appropriate layout, ginagamit dito yung high and low forecast para sa opening year. So, ito ay ina-undertake sa pamamagitan ng mga factors na nandito sa table natin. So, meron tayo ditong carriageway type, AADT range, which is the opening year, and the quality of access. So, meron tayo ditong mga given na LGVs, ito yung light goods vehicles, OGV, OGV2, and PSB. Ito yung makakasagupan natin kapag nagsosolve tayo ng problem. So, mag-solve tayo ng problem. Given dun sa problem na meron daw tayong 15,000 vehicles. So, 12,450 cars, 1,350 LGB, OGV ay 600, OGV2 ay 450 at PSB ay 150. So, kukunin naman natin yung high growth at low growth sa pagitan ng 2000 to 2006 doon sa 5 categories ng cars. Yung LGV, yung OGV1, OGV2 at PSB. Pagkatapos nun, madedetermine natin. Then, isa-select natin doon sa table kung ano ba yung appropriate. Sa case na ito, since yung high growth rate over the 4 years ay 8.2% at ang low rate ay 5.5%, so ang wide single carriageway na 2 by 5.0 meter na nag-range from 10,000 to 18,000 ang most appropriate standard.